said no matter which dimension you have, starting with 2, you always get Hilbert space, Edder space. So, to sum up, suddenly Edder spaces seem to appear everywhere in unrelated areas of topology and set theory, which is nice. Now, I changed the theme of the talk. Let's go to homogeneity, but I will come back to Edder spaces. I don't have to tell this audience what a homogeneous space is, so I wrote. And powers of homogeneous spaces are, of course, homogeneous. That's trivial. And, however, it's possible for homogeneity to hold in a power of non-homogeneous vector spaces. And the most famous example of that is the theorem of Keller. He proved in 1931 that the Hilbert cube is homogeneous. If you take the product of Cantor-Riemann intervals and they are not homogeneous, and then suddenly the space that you get is much nicer with respect to homogeneity properties. At that time, his result was not really valued very highly. I guess, but it's my fantasy because I don't know, all these people from that time are already dead, so nobody can tell me. But I guess they thought of it as a curious result, interesting, curious, etc. But then in the 60s it was, say, rediscovered by Dick Anderson, and when he started at the field of infinite dimensional topology, and this was his motivating result. And he found it very interesting. He found his own proof. Keller used convexity theorems, and he found a nice proof, walking around corners, and then he started at the field of infinite dimensional topology. So, say, 30 years later, suddenly somebody finds your paper and says, oh, that's great, so don't be disappointed if nobody knows you. I think Fitzpatrick, but I'm not sure, but Gary will know, I think. And he asked, is there a zero-dimensional subspace X of the real line R such that the countable infinite product is not homogeneous? Somewhere I read this, but I don't remember where, so maybe it's totally wrong, but you know it.
Okay.
Was this the?
Ben and Joe Housewan were asking about that, and I had a role in popularizing it.
Absolutely. It grew in 1990. New classical problem is the countable infinite product X to the omega of any zero-dimensional first countable space homogeneous. It was identified by you as a new classical problem, and it was a very nice and very interesting problem. It was because it belongs to the past now, because it has been solved. Sierpinski proved in 1932 there is a zero-dimensional rigid subspace of the real line. But what means a rigid? A rigid means you have no homeomorphisms except for the identity. It means you cannot do anything in that space. There is no movement. At least in Keller's theorem, he proved that the Hilbert cube is homogeneous. In the interval, you can push points around, but in a rigid space, you can do anything. So for such a space, why would X to the omega be a homogeneous space? No movement whatsoever. Maybe X to the omega is rigid also. No, it's not rigid, because if you look at omega, you can always interchange the coordinates. Coordinate permutations are always there. So if you take any space whatsoever and you raise it to any power whatsoever, you will never get a rigid space because you can permute coordinates. So a rigid space, I already told you. Oh, this I also already told you. And so the result of Sierpinski suggests that maybe this is all there is for such a product. Because why would there be another homeomorphism than a coordinate permutation for such a bad space? Well, Lawrence proved in 1998 using highly non-trivial continuous families of coordinate permutations. You can move them around, but you can let them vary in a continuous way. And that was the brilliant idea of Lawrence. And he answered Fitzpatrick's problem in the affirmative, but this is ridiculous because I said, is there a space X for which the infinite product is not homogeneous? So I should have written here, he answered the negation of this problem in the affirmative. He proved that if you take any subspace, any zero-dimensional subspace in the real line, its countable infinite product is a homogeneous space. So this is even true for this very rigid, this very bad subspace that Sierpinski constructed in 1932. X to the power of omega is homogeneous. And Dow and Pearl generalized it to answer Gary's classical problem, and they proved if X is a zero-dimensional first countable space, then its countable infinite product is a homogeneous space.
So I did not think you actually beat Brian to
I don't see
zero
already.
communication.
No, this was
It's
proved
before, but it appeared after.
Yes. Here's the definition of a partial permutation. Let me not go into that. And this is copied from the Dow and Pearl paper. I will not go over it, but I will point you to where the permutations are. So you have a zero-dimensional subspace of the Cantor set. They work in the Cantor set, but that's of course the same system as in the real line. If you stick to the zero-dimensional spaces, you take 2 points in the countable infinite product, and you have a subspace X between B and its closure, then you can find a homeomorphism of the countable infinite product and partial permutations H0 of n, so that good things happen. F sends X onto Y, so that's homogeneity. And here you see the permutations coming. You see here there is a neighborhood, and there is a permutation. And what does F do? It permutes the coordinates. Right? And there is some other junk going on there, but here you see it permutes coordinates. Okay, a very complicated result with a complicated proof, very nice result also. And that's the Dow and Pearl proof of the Gary's classical problem. So, if you look at the proof, you will see that for every homeomorphism F that the proof gives you, there is a co-meager subset of X to the infinity, such that at every point F acts as a full permutation of the coordinates. This is what the proof gives you. It does not state it explicitly, but if you go over the proof, you will see a very big subspace. Really, it's a full permutation all the time. And it varies in a continuous way. It has to be, because otherwise you cannot get a continuous action at the end. So Medini, myself, and Domsky proved this year that it is consistent that there is a zero-dimensional bare subspace Z of the real line R, which satisfies the following conditions. For every homeomorphism, you have a co-meager subset C of Z to the omega, so that you, on that co-meager subset, you have these coordinate permutations. and they vary in a continuous way. So in a sense, it shows that this is rigid in this category of spaces. If you look at x to the infinity, you apparently have always such type of homeomorphisms, and we prove you can have such a space where they are the only ones. So it's in this category, you can think about it as a rigid object. And so it was very good that Down and Pearl found these homeomorphisms because they are the only ones that you can get. And so the space Z is the set of omega 1 common reals viewed as a subset of the Cantor set. So in a sense, and you can debate in what sense exactly, but in a sense the Lorentz-Dow-Pearl theorem is sharp. You can't do any better. And that was the reason why we were interested in this result. So back to Edder spaces. I started with Edder spaces, and I then went to homogeneity, and so let's go back to Edder spaces. Of course, that was in the title of my talk. So let me remind you again, you build the Edder space on X, you look at all vectors in a real Hilbert space. Every coordinate of that vector belongs to X. That's the Edder's time space on X, and it seems very similar to the countable infinite product of X to the infinity. There is one unpleasant problem. They are very often one-dimensional, and so it makes a difference. It's of course not equal to the infinite product. If you choose a vector here, where so if you choose some point in this product so that its coordinates to get larger and larger norms, you have a problem. So not all points from the infinite product are in the Edder space. There are differences, and there should be differences, because E of X is one-dimensional, not always, but usually. And this space is of course always zero-dimensional. So, but they are very similar, it seems. Topologically also, they are very similar. So we started, Klaus-Peter Hart and I started to be thinking, so maybe we can do the same thing as in the Dow and Pearl theorem and permute the coordinates. And maybe we can prove that these guys are always homogeneous spaces. This was the starting point. And it didn't seem to be a stupid approach, because also here you can permute coordinates. If you move them around, you get an isometry of Hilbert space. You can do the same thing, and these isometries are they preserve this Edder space built on X. So there is a lot of the same things going on, and it was a good attempt to say, well, maybe we can use the same ideas to prove homogeneity for these spaces. And as I said it already, there are very delicate differences, of course, and because these spaces are one-dimensional, and so you have to be really a little careful. So, E of the rationals, it is a subgroup of Hilbert space. So that's good. It's a homogeneous space. E of the irrationals, it's a closed subset. It's certainly not a subgroup. Remember, yes? No, it's not closed. E of the convergent sequence, which is topologically homomorphic to E of P, that's a closed subset and not a subgroup. So it's not clear that it is a homogeneous space. And E of P is a dense subset, so it's not a subgroup. But I hope I told you, yes, I told you that Kawamura and his co-authors proved it's a countable dense homogeneous space, and in particular it's a homogeneous space. So this space is also homogeneous. It's comforting to know that the basic examples at least work. They give you homogeneous spaces, and if you work a little bit on it, you can prove that actually E of P is also a topological group. And E of X may be homogeneous even when X itself is not, because I said E of the convergent sequence is topologically homomorphic to E of the irrational numbers, and that's a homogeneous space. So that's in a sense similar to Keller's theorem. If you take the infinite product of integrals, you get a homogeneous space, and it's also similar to the Lorentz-Dow-Pearl theorem. If you take any subspace of the real line as zero-dimensional, homogeneous or not, the infinite product is a homogeneous space. So this happens here also. Blowing it up in this way may result in a homogeneous space. And this is what I said already